which is nothing but converted to energy equation or Bernoulli principle. So it is derived based on F is equal to ma. So that is for ideal fluid flows. Now for real fluid flows, the basic difference is, while we have neglected the shear stresses in the case of ideal fluid flows because of the absence of viscosity, the same cannot be considered here because it is a real fluid, so it has certain viscosity, and due to that viscosity, the shear stresses will also be present. So therefore, while developing the equations for real fluids, we have to take into consideration the forces due to shear stresses. So that is the basic difference. But for that, the same procedure, everything will be same. Oh, this is the syllabus for Unit 2. The basic difference between real and ideal flows, and what are the practical problems associated with laminar flow. So before developing or deriving the governing equations, we will consider something about the forces on fluid elements. So I already told about the presence of shear stress, and I will introduce to you what is known as a stress tensor and the relationship between stresses and the strain rates for viscous flow. See, if you recall your fundamental knowledge of Newton's law of viscosity, it says that tau is equal to mu du by dy. What is the tau? Tau is the shear stress. And what is the what is dV by dy? dV by dy is nothing but the deformation or the strain. So that is for a simple case of two-dimensional flow. Now here what we consider is the most general case where the velocities exist in x, y, z directions. So there will be deformations in x, y direction, z directions, which causes strains in all the three directions, and which further leads to shear stresses. So this aspect we will consider. Then what we do is, after developing the governing equations, we take those equations and try to find out the exact solutions for some of the practical problems. So the practical problems that are included in your syllabus are the flow between parallel plates with and without pressure gradient, the distribution of velocity and shear stress in between those plates. So these are called as Poiseuille and Piatti flows. Then we have flow in annular space and flow between rotating cylinders. These two come under the category of flow through pipes, pipe problems. Then we have two special cases. One special case is flow past inclined planes, and the other special case are Stokes first and Stokes second problems. So these are flow near a sudden accelerated plate and an oscillating plate. See, we consider the flow past plate. Initially, the plate is stationary. Then suddenly it is accelerated. So then how the flow pattern changes. Similarly, there is another case where there is a plate which will be oscillating. So what are the governing equations? What is the solution for that? So these are the things which we will consider. So here I have given the difference between the real and ideal flows. So this already I have explained just now. The potential flows considered earlier signify the ideal fluid flow cases where the viscosity is absent. However, many of the practical flows are real fluid flows and cannot be analyzed using the potential flow concepts. Precisely speaking, the effect of viscosity not only brings in a change in the boundary conditions, but also in including additional shear stress, which were earlier considered absent. In the case of ideal fluid flow, shear stresses are considered absent. Thus, the Euler equations of motion derived earlier fail to provide a solution for analysis of the viscous flow, or which is also called as laminar flow problems. So this suggests that certain modifications, such as introduction of shear stress terms, is needed in the general equations of motion. However, one point that must be clearly understood is that the basis for the derivation of governing equation of motion for laminar flow problem is also Newton's law of motion, second law of motion. That is F is equal to ma. What we had done earlier was we had divided both sides by m. So force per unit mass is equal to acceleration. So that is what we have considered. So here also the same approach will follow. Newton's law, second law of motion will consider. Now these Navier-Stokes equations represents Newton's second law of motion as applied to viscous flow of a Newtonian fluid. Newtonian fluid means the fluids which obey Newton's law of viscosity. The fluid is considered to be incompressible and of constant viscosity. So the only assumption which we make is that it is an incompressible flow. That is, rho is constant. Mass density rho is constant. Then the viscosity is also constant. It will not change from point to point. So these are the two main assumptions involved. Similar to continuity equations, there are multiple ways to derive the Navier-Stokes equations. In the present juncture, the derivation is carried out starting with a fluid particle and applying Newton's second law of motion. Thus, the result will be non-conservation form. There is another method by which we can also derive the so-called momentum principle, or is with the help of what is known as a Reynolds transport theorem. So this, of course, I will not be considering. It will be considered while we derive the momentum principle. So this is the nomenclature which we have followed for normal and tangential stresses. So it is these shear stresses which are now considered in addition to the pressure, forces due to pressure, that is normal stress, and body force. These are 12 components, 2 on each face. There are 6 faces. So you will get 6 into 2, 12 shear stress terms. So this is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? Yeah. Now, As usual, what we do is we'll select a fluid particle which is having 1, 2, 3, 4, 5, 6 surfaces, and the dimensions are delta x, delta y, delta z. And considering Cartesian coordinates, this is x, this is y, and this is z. Now, assume the dimensions are infinitesimal and that the particle is at the position x, y, z. The central point coordinates of the central point are x, y, z at any particular instant of time. Now, what we do is we will apply Newton's second law. Now, the forces acting on the element are surface forces and body forces. Again, the surface forces are due to pressure and shear stress. Now, here this is the additional thing we get. And of course, the body force, and we will also consider the lone body force as the weight of the element. So these three we will consider. Now this is what we have done in the previous case also. From Newton's second law, this is what we have written. F is equal to ma. So that means sum of all forces on the particle is should be equal to the product of mass and acceleration. So sum of body force plus sum of surface force must be equal to mass into acceleration. Now, mass into acceleration, mass is written by the product of rho and volume, and A is the acceleration. So, using the notation of W for body force, Fp for surface force, yes, for pressure force, which is a surface force, and an additional force Fs. This is due to shear stresses due to the presence of viscosity. So that must be equal to rho V volume and dV by dt, where V is the velocity in any direction. V is the velocity in any direction. Also here I have used the small letter to indicate, in fact it should have been written and also these are also vectors. So that means this equation is written in vector notation will be actually different in x direction and it will different in y direction and different in z direction. When we are considering x direction, we will consider the forces acting in x direction on all the two surfaces due to this as well as this. And here we will write small u. And here we will write small v, which represents the velocity in y direction. And here we will write small w, which represents the velocity in z direction. Now, the procedure which we have followed for real fluid flow cases, ideal fluid flow cases, is that we have taken the pressure at the center point as P, and we have written the pressure here, or the force here is P minus something into area, and here P plus something into area. So that is what we have written. So this is, here you can see P, this indicates that the pressure on the surface which is located at x minus delta 2. See the coordinates of this point are x, y, z. So this surface is located at a distance of delta x by 2. So this is referred as x minus delta x by 2 plane. So pressure on the surface at x minus delta x by 2 minus the pressure on the surface x plus delta x by 2 multiplied by the area. The area of the plane in x direction is delta by delta z. Now this I is the unit vector indicating that when we are considering x direction, this will give me the force in x direction. So similarly, by simplifying this, we will get this expression. Similar expression we got for ideal fluid also. So now if I consider all the three directions, I will be now getting so the force due to pressure on the element is, it is written in the vector form. So minus dou p by dou x into delta x delta by delta z. This will be only, this term only will come when we are writing the force equation in x direction. And this term will come only when we are writing the force equation this will come in x direction only, and this will come in y direction, and this will come in z direction. So this what I can write is Fp is equal to minus dou p by dou x I dou P by dou Y J, dou P by dou Z K into delta X, delta Y, delta Z are constant. So I can bring out of this. So in vector form, this is called as gradient. This is gradient of P. That is dou P by dou X into I plus dou P by dou Y into J plus dou P by dou Z into K. That means in X direction, it will be minus dou P by dou X, delta Y, delta Z. So if I want to write the force due to pressure in X direction, this will be simply dou P by dou X into, I will use the symbol delta V to indicate the total volume. So in Y direction, force due to pressure in Y direction is equal to, of course, minus is there, minus dou P by dou Y into delta V, and in Z direction, FVZ minus dou P by dou Z into delta V. So this is what we get in Z direction. So this is only one part, that is surface force due to pressure. Now we have the shear. So this is what we have to do. Now the shear force is the net force on the fluid particle due to shear stresses. Now shear stress is caused by viscous effects and is represented mathematically as in figure below. See, this I have already shown. So this is what we used in, see, actually here we have used, this is sigma. This is sigma. This is sigma. Actually, this figure I had taken from some other book. So they have used that notation. Only tau for all stresses. But anyhow, so their force is the net force on fluid particle due to shear stresses. Shear stress is caused by viscosity. Now this figure shows that each phase of the fluid particle has three stress components, and For example, the positive X phases has three stress components, which are sigma xx, tau xy, and tau xz. This point, of course, I have already discussed while explaining you about the ideal fluid flow or deriving the Euler's equation. So let me not repeat it here. See here, the stresses, this is what you have to know. Sigma xx, sigma yy, sigma zz are due to the velocity gradients and are different from the pressure forces. See, while deriving for the ideal fluid flow case, we have taken sigma xx is the stress and we have taken it in terms of P. But now here, in addition to the pressure term, we will get this sigma xx, which is contribution due to shear stress. All the three are due to shear stress. Two will be acting parallel to the surface and one normal to the surface, right? So now to distinguish the earlier notation of sigma y, sigma xx, sigma yy, sigma zz, which we have used for pressure, now I have used this notation of tau zz, tau xx, and tau yy in place of sigma xx, sigma yy, sigma zz to indicate that due to shear stresses, tangential stresses or shear stresses. So that is why I had taken this figure and this notation, right? So same, this particular one is similar to the earlier one. Only thing, earlier for ideal fluid flow case, we were having only sigma xx, and of course these were shown but not considered. Only for the sake of notation, at that time I have shown this table, and no, only these were considered. So these were not considered in the previous case. Okay. Now, the important point here is that I will now represent the shear force in terms of the shear stresses as the gradients. See, what we have done earlier we had written it is dou P by dou X, dou P by dou Y, dou P by dou Z. Only three terms we got. Now what we'll have, in addition to dou P by dou X, in X direction, we are having this, and this also. So this term is again a gradient. See, we have considered P plus something minus P minus something into area. So same way here stress. So the stress at the center is this. So at the outer surface it will be tau xx minus something, and at the outer face it will be tau xx plus something. So the net force will be this minus this. So which we will get as this term into product of delta x, delta y, delta z. This is due to tau xx. Similarly, due to tau xy also, you will get tau xy minus something at the outer inner face, tau xy plus something, and the difference will be the gradient. So like that, we'll get this is the expression for force due to shear stresses, surface force due to viscosity, due to shear. This is the next direction. And this is the one for y direction. And this is the one for z direction. So in the vector form, as we have written earlier, so here we have written in this form. So similar notation we are using here, and we have written here. So we have two surface forces, one due to pressure and the other due to shear stresses. So now these are combined. Combine the terms. Substitute shear force and pressure force into Newton's second law of motion. So F is equal to ma, or m is rho and this is v is equal to this is body force and this is the stress part. Now what we do is so this is what this here. Okay. So this is the surface force. Now this is this part. Now this is written considering the pressure and the shear stress. So this is due to pressure and this is due to viscosity. So now this equation after simplification will take this shape. Only thing is here I would have used this word, this. So this is the simple equation. In fact, this is not one equation. This is set of three equations. One in x direction, one in y direction, one in z direction. When we write x direction, here we will get u. And here we will get 0 because x direction is this and maybe y direction is this and this is z direction. If suppose we consider z direction is vertical, then this will become y direction and this term will be present only in the vertical direction, whether it is y or z direction. So when we are considering x, here you will get u. So here you will get u. And here you will get 0 And here you will get dou p by dou x. And of course, this will be containing this term. So there will be 1, 2, 3 terms due to shear stress. So here you will be having 3 terms. These are actually 3 terms, and this is 1 term, and this will be 1 term, but that 1 term may be 0 or G, and this is 1 term. So you will have total 5 terms on the right hand side, and on the left hand side you will have local acceleration plus 3 terms due to convective acceleration. So on the left hand side there will be 4 terms, and on the right hand side there will be 5 terms. So this is what we get. So in x direction, you can see u, 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 u. This is dou u by dou t, which is local acceleration, and dou u by dou x, dou u by dou y, dou u by dou z. This is, and convective acceleration. So this is body force. So, and this is pressure term, and this is stress term. So we'll get in x direction, y direction, and z direction these equations. Now let me just, okay. It may be noted that the last 3 convective terms on right hand side are highly nonlinear. See, these terms, because there is a u dou w by dou x, u dou v by dou x, u dou u by dou x. See, this is a second order term. So they complicate the issue. So a simplification is possible considering an incompressible flow of Newtonian fluid where the viscous stresses are proportional to the element, on the right hand side. On the right hand side, these 3 terms, these are also nonlinear. The left hand side 3 terms are also nonlinear, but these are very complicated. These are complicated. The reason is the tau itself is the rate of change of deformation. Tau is equal to mu du by dy. So if I replace tau by du by dy, say for example, then it will become dou square by dou x square, or dou square by dou x dou y, or dou square by dou x dou z. Like that, the three terms on the right hand side, the last three terms on the right hand side will be del squared terms. Dou square by dou x square, like that you will get. So now what we do is, we will consider a simplification suggested by Stokes. Stokes in 1845 figured a way to write the stress tensor in terms of the rate of strain tensor of the flowing fluid, and these are known as Stokes constitutive laws. So he has written that these are Stokes constitutive laws. So these are the expressions: tau xx, tau yy, tau zz, tau xy, which is also equal to tau yx, tau zy, which is equal to tau yz, and tau xz, which is equal to tau xz. So these are the terms. Tau xy is equal to like this. So these are now introduced in this. Tau xx, tau xy we have. So these are introduced. And then they are introduced here. So we will get this. So this is the term we'll get. The above equations are second order. See, dou square. So this is second order, first degree, non-linear, because u dou u, v dou v. Here w is missing. W dou w. So this is non-linear. So this is non-linear, second order, and partial differential equation. And these are called the Navier-Stokes equations. And in vector form, they are written like this. See, I have been writing small v here. Now I have corrected it. And rho dv by dt is equal to rho g bar plus delta p plus mu del. This is called as the Laplacian del square of v bar. Okay, now I will just stop here 1 minute. Come on. Who is the person who has expressed the doubt?
Sir, 01.
Okay. No.
I'm audible, sir.
Yeah, you are audible. Okay. What is your doubt?
Sir, why it is del x by 2, sir? Why you considered in x direction?
What I told, the pressure at the central point is P. Okay. No, have you followed Euler's equation which we had derived earlier?
Yes, sir.
Then why don't you go there and see how we got the expression for force
No, sir,
on the
I'm
inner
asking
plane?
x plus del x by 2. It's a
No,
by function of
1
p.
minute. See, that indicates P at x minus at delta x by 2. The symbol which I have used indicates 1 minute. Okay, I will go to the PPT. That is better. See here, are you seeing this, which I have highlighted?
Yes, sir.
So this indicates the P at x minus delta x by 2 into area minus the pressure at x plus delta x by 2 into area. That is the
Net force
net.
is
Huh?
zero, sir.
Hmm? What?
Sir, then the stress acts both on both sides. Then net force will be zero.
See, it is the pressure. Listen carefully. It is the pressure on the face x minus delta x by 2, and it is the pressure on the face x plus delta x by 2. What is the pressure on the face? That I told you, you are not listened properly. See, this one is the pressure at the center minus dou P
Change in pressure
by dou
in x
x
direction.
into delta x by 2. And this is P
Okay, sir. I got, sir. My notation.
plus. See, you have to follow that point. See, everything.
Yes, sir. Notation is change in
Ah,
pressure with respect to x direction.
that indicates. See, this is the notation normally we use. This you should know.
So I don't know.
P at x minus delta x by 2. P at this you should know. Anyhow. Now is it clear?
Yes, sir.
Yes, any more doubts? Any more doubts? Okay. Now tomorrow we will have a class, and we'll work out the problems. So I have already sent you the problem sheet. So you note down problem 4.1, 4.2, 4.3, 4.4, and 4.9. You work out, and the doubts you ask tomorrow in the class. Then 4.11, 4.12, 4.13. These three problems are assignment problems. So 4.1, 4.2, 4.3, 4.4, 4.9 are the problems to be worked out in tomorrow's class. So all of you try to work out, and if you are stuck up at any stage, first you explain what you have done, and then I will be clarifying them. So tomorrow again at 3 o'clock we will meet. Any doubts further?